start?
Sure. I wasn't sure because this was an AGI seminar and I just wasn't sure with all the logistics. So please go ahead. Yeah.
Yeah, so normally this would be Dr. Schultz that does this, but I'm happy to step in here at the last minute. Dr. Noel Schultz and I are the co-directors of the Advanced Grid Institute. And the Advanced Grid Institute is a joint project between Washington State University and the Pacific Northwest National Laboratory. And as part of the ESIC weekly seminar series, the AGI is pleased to host a seminar once a month. And so for this month, we'd like to feature a project that is jointly supported by both the Pacific Northwest National Laboratory and Washington State University in terms of collaborative research activities. And so the title of the project is called GridAPPS-D, a standard-based platform for advanced distribution system operations. And so you'll be hearing a lot more about that project over the next hour. And our leadoff presenter is Alexander Anderson. So Alex, you want to take it away?
Thank you. I'm going to be introducing the GridAPPS-D program, the development platform, and some of the standards-based modeling approaches that we have been developing and promoting as part of the GridAPPS-D program. And then I am going to hand it over to Andy Reiman. GridAPPS-D is focused on enabling a decarbonized future by supporting the next generation of distributed apps and ADMS systems through standards-based data integration, and it provides a development environment that enables distribution projects to remain within a single platform from the initial concept proposal to utility demonstration and commercialization in collaboration with a ADMS vendor. It is a DOE and OE project led by PNNL with a number of partners from industry, utilities, and other research institutes. You can see here an overview of our core industry advisory board and collaborators. Modern Grid Solutions, INCSYS, WSU, and NREL have been key contributors to development of the GridAPPS-D platform applications and models. And we have been working together to promote a standards-based approach that is focusing on data integration, and a key concept is the separation of data integration from new app functionalities. Traditionally, when you are trying to bring an ADMS application into a utility, the biggest burden is not development of the new functionality, but integration of that new functionality with the existing ADMS system, with the existing databases, with the existing utility models. And so for GridAPPS-D, we have developed a standards-based reference architecture and an open source platform that serves as a reference implementation of that architecture. And within the environment, applications are portable across any power system model or any compatible ADMS integration with the GridAPPS-D platform without any modification to the application code. And we have an open API with standardized interfaces to models, databases, measurements, equipment controls, forecast, and more data streams. And one of the powerful components of GridAPPS-D is the more developers we have join and use the platform, the more data streams we get, and the more benefits are available to other developers. One of the ongoing efforts that Andy is going to be talking about in more detail in the next section is the introduction of distributed applications for management and control in an environment with high DER penetration and transactive markets in a fully distributed manner. GridAPPS-D also offers a full suite of power system models based on the Common Information Model format, SIM, and we have, as part of that program, introduced a lot of extensions into SIM, which are now being reviewed and integrated into the upcoming SIM 18 model release. I'm going to dive into a quick technical overview of the GridAPPS-D platform. It is an open source platform and development environment with pre-built Python and Java libraries for most API tasks, such as getting the power system model, getting incoming data streams, managing a co-simulation. All of those tasks are handled through a standardized API. There are numerous shared services such as state estimator, topology processor, and alarm service, device protocol services for external links such as DNP3. We use Docker to containerize all of the applications and services and databases in a GridAPPS-D installation. And it is any application that is built in GridAPPS-D is able to use the API and the shared services to interface with other vendor ADMS systems. So if you are building a Flizzr application and then want to demonstrate, but don't want to spend the effort to build a user interface, you can use GridAPPS-D in the DNP3 service, connect it up to, say, a surveillant interface, and use the surveillant user interface to show your Flizzr application working in real time. We use the Common Information Model for all of the network models and messages, and I'm going to be talking about some of the interesting aspects of building a fully compliant SIM application shortly. Many of you are more familiar with the power systems analysis type environment, such as PSSE, PSLF, OpenDSS, GridLab-D. These types of power flow solvers, you maybe build, you directly control it from within the interface, or maybe you use a connection to a MATLAB script or a Python script to get your power flow results. GridAPPS-D is a very different paradigm. It is focused on live data streams and aggregating those data streams and then making them available in real time to ADMS applications. And the core of it is the grid optics, or GOS for short, message bus, and then the underlying SIM-based messages. And this allows us in a very efficient manner to provide AMI data, load data where we do a thermal simulation of house HVAC units, water heater units, those types of in-home appliances, live weather data, SCADA data coming in from a RTU, and with the core development process, because before you work with live data streams, you need to be able to make sure your app works correctly. We have a powerful real-time co-simulation environment. All of that data gets fed into the GridAPPS-D platform and is made available to services and applications. Those work in a publish-subscribe paradigm and issue control messages and output messages via DNP3 or direct controls of equipment, inverter, microgrids. And everything that happens within the GridAPPS-D platform gets written to a series of time series databases and is then available to be queried after the simulation run or after the real-time data has been logged. There have been a number of applications and services that have been developed and are available in various states of technology readiness levels. PNNL, NREL, and WSU have been the core application developers up to this point, and most of these applications are available with the source code on GitHub. Data integration provided by the GridAPPS-D platform is able to provide a very powerful development environment, and that is coupled with a web-based graphic user interface where you can write your application code and test it against a co-simulation in real time. Here in the graphic, you can see a simple Python code which is sending sim difference messages to open and close a switch repeatedly. Just a very basic script. And you can see that switch opening and closing in real time and the switch message status being published back to that Python script. A couple more snapshots of the user interface. We're able to show outages, equipment statuses, strip charts of the various equipment measurements so you can get voltage, power, position measurement, tap position, switch positions. All of those are able to be plotted in real time. You can control most equipment through the user interface in a manner similar to a dispatcher training simulator. You can also view alarms and other status messages through the Alarms tab or the simulation status logs. The key portion of GridAPPS-D that makes it so powerful to researchers is the accelerated application development environment. And GridAPPS-D has made major progress in reducing the effort for building SIM-compliant applications through the use of a standardized API and reusable code blocks and services. So there are numerous services that you can leverage, such as Snapshot Power Flow Service, Topology Processor Service. So multiple applications can use the topology service and get real-time topology without having to build their own topology processor. Similarly, the GridAPPS-D toolbox is creating sets of reusable code that you can just copy and paste into your application. And we are continuing to add new functionalities on an ongoing basis. We have a monthly toolbox user group meeting where app developers can come in and say, I need this particular functionality or this particular service for my research or for my application that I'm trying to build with this utility. And if there are two or more development teams that need a particular functionality, then our internal toolbox team will help build reusable code that can be used by both projects. There's also extensive documentation and interactive Python training available through the GridAPPS-D documentation website. We also have a Q&A forum and a issues board for asking general questions or for reporting bugs in the platform. I'm going to talk briefly about the common information model and why we chose to take a SIM-based approach to all of the power system modeling and power system information messages within GridAPPS-D. The motivation comes from the different approaches to data integration. The first is a vertically integrated single vendor EMS or ADMS platform. If you go and buy a complete EMS and ADMS package from GE or Siemens or ABB, you're going to get this vertically stacked system. It uses a proprietary data format and a proprietary API, and the vendor typically has done all of the hard data integration work so that a GE Blizzard application is going to work perfectly fine with the GE outage management system. They are connected together by the vendor using that proprietary data format. However, as soon as you try to get a second application from a different vendor, now you end up in this middle section where you have to do custom application integration with custom adapters between each application and each database. This approach is unfortunately still very much the common practice within utilities and industry, and it is very costly and very fragile. Within GridAPPS-D, we have been pursuing a third paradigm, where you use a standards-based platform using an agreed-upon information model. That information model provides a consensus-based vocabulary for explaining and representing everything within the power system model in a standardized format. And then each application and each service only needs to communicate with that API and across that shared message bus. You do not have to build any application-to-application adapters. A bit about the Common Information Model. It's an open source canonical information model for all aspects of a utility business. It's maintained and published by the SIM users group under an Apache clause and maps to a set of IEC standards. You do not have to purchase the IEC standards to use the information model. That's one of the misconceptions that people often run into. And SIM provides a fully standardized way of representing and exchanging data and power system models. There is an initially steep learning curve to learning the class names. So you need to remember that a line is called AC line segment, and it has a certain set of properties like conductor length and so on. And so once you get over that initial learning curve of the SIM naming, then it is quite easy to work with. Another unique concept to SIM is the Master Resource Identifier, or MRID for short. And it's a 32-character string. It's not human readable. It's something that is used by the applications and databases in the background. And it is used to track all of the equipment, measurements, and data points. You should never hard code MRIDs into your application. Rule number 1 of working with SIM. You should be working with the database that stores the information model. You do a very fast query in real time. That gives you the MRIDs of all of the electrical components, the impedances, the ratings, and so on. And you use that information to run your power system analysis. Another modeling aspect that is new to a number of developers is that SIM uses explicit modeling of nodes and terminals, and you need to keep in mind whether different pieces of equipment use 1, 2, or 3 connectivity nodes to represent that piece of equipment. To help with that learning curve, we are putting out a pair of modeling guides that will be made available publicly. The first one explains the philosophy of data integration and data exchange using SIM, and then the second provides a detailed guide to the SIM classes based on the new SIM 18 draft. We use a tool called SimHub. It is available freely on GitHub to do all management of models. It is able to import SIM, Synergy, OpenDSS, and other types of model formats, convert it into SimXML, and then that is fed into the GridAPPS-D platform, into the BlazeGraph triple store database, and is then made available for applications and for co-simulation. This is the general flowchart of importing a new power system model if you need to work with a new power system model, such as if you're working with a utility and need to import a sensitive utility model. We have a method for doing that, importing it, creating measurements, creating houses for the thermal co-simulation, and then running it in the GridAPPS-D platform. We also have a large collection of IEEE, NVEL, and EPRI models that are available. And I'm going to talk briefly about the 9500 node model, which is a new power system model that WSU, PNNL, and Inksys Modern Grid Solutions 2 industry collaborators. The 4 of us have developed this new power system model as the representative test case for the anticipated past, present, and future of distribution systems with over 11 megawatts of distributed energy resources, all modeled using the common information format. It is derived from the original 8500 node model. We added 3 substations and a 69 kV subtransmission network with explicit modeling of all reclosers, sectionalizers, and substation breakers to provide realistic switching information. We also have 180 inverters and 11 megawatts of distributed resources divided into 7 microgrids or potential microgrids. We have 3 dedicated microgrids and 4 that can be formed dynamically from the large-scale DERs and the network. There are multiple open switches that can be used for topology reconfiguration and fuzzer applications, and the model can be used to create realistic scripts of common utility operations, transitioning from blue sky to severe storm conditions. We are going to be making those particular scenarios available in the near future. These scenarios can also be loaded into the GridAPPS-D test manager and used for testing your application against faults, communication outages, and other scripted events. Within this development environment, you can conduct offline power flow studies, microgrid projects, and application developments on your own local system, or you can also leverage facilities such as the PNNL Electricity Infrastructure Operations Center, or EIOC for short, which we have used for demonstration of some of the GridAPPS-D applications with utility operators and operations engineers from Avista, City of Richland, Benton, POD, and so on. The 9500 node model is available on GitHub and is currently being reviewed by the PES Test Feeders Working Group for inclusion as a new IEEE test case and the successor of the original IEEE 8500 node model. I am now going to hand it over to Andy, who is going to give an introduction of the distributed application effort within the GridAPPS-D program. Andy is the application area lead within the GridAPPS-D program and the systems tools team lead at PNNL.
Thanks, Alexander. So I was not able to connect to Teams today. I'm calling in from a hotel room in ISGT, as I think Alexander and others are. So Alexander has kindly offered to keep sharing the slides while I talk, and I'll do my best to stay synchronized, but I'm looking at a local copy. So as Alexander mentioned, I will be talking about a distributed applications architecture that we've developed for GridAPPS-D. Alexander, can you go to the first content slide if you're not there already?
Just got there.
All right, thanks. So GridAPPS-D, as Alexander spent some time describing, uses a platform approach to data integration. So we have applications separated from a data integration layer by a standardized API. And the advantages of this include portability and reusability of code. Here we have an example of a platformized distribution system where you might have applications that have cognizant control over the distribution level at the control systems or control center point. So that would be one copy of the application for the whole distribution system. And then the second red layer, we show applications that are substation specific. So examples of this might include more localized coordination and control, or state estimation may apply, may be calculated at the local level. and then transmitted back to the centralized layer within the distribution system. And then layer number 3, we have device operations within the feeder. So individual devices may be controlled, they may be coordinated through distributed energy resource management systems, or DERMS, but there are certainly local controls that control individual devices as well. So all of these layers can benefit from talking with each other and from a platform architecture that supports multiple layers and different agents. Can you go to the next slide, Alexander?
Just did.
Here are, thanks. So here are some reasons why distributed applications may be advantageous. First, resilience. So applications that are distributed may be able to continue to function if part of the communications system or part of the power system goes offline. So there may be local areas that agents are controlling that may work in an island, or may be powered from substations that are still active while others are out. And the distributed app architecture allows apps to function with the pieces that are remaining during a partial outage or incremental recovery.
Also from the media sensor.
If that was a question, I didn't get it. I don't think it was, so I'll move on, but interrupt me if it wasn't. Democratization is another reason. Agents at the grid edge can participate in a distributed architecture more easily than they can from a centralized architecture. If the agent doesn't require full access to the full system level API, then it can interact with local devices only, which feeds nicely into compartmentalization, where agents can be limited to a view of their kind of need to know area to perform local functions. And this can help sharing information across ownership boundaries while allowing proprietary or private information to remain outside of the centralized system. One other advantage that isn't listed explicitly here is that data rates can be really high at the grid edge. So any processing of data that can occur at the grid edge can also be advantageous in a lot of cases. Can you go to the next slide, Alexander?
Yes.
Thanks. So I think Alexander introduced this, but I'll highlight a couple of key features on the base GridAPPS-D architecture. You can see applications interconnected at the top through an interface in the red central block. And then we have the standards-based data bus in purple below that. And then there's a simulator in the standard version of GridAPPS-D that emulates a real world. This simulator allows applications to be developed using an underlying simulation, but using the same interface that they might be able to use in a deployed version. And I'll come back to that later. But the key here is that applications are interacting again with the over a standards-based API and a message bus underneath. So if you go to the next slide, we can look at some architectures of distributed applications. First, we have a hierarchical architecture where we have field devices at the bottom, which may be connected to field buses, and more on field buses later. Distributed agents can be associated with different layers in the distribution system. So we have the concept of in GridAPPS-D of a secondary distribution secondary area and a switch delimited area, and then a feeder area, all within the distribution system unified area. We also have a peer-to-peer architecture where agents that are at the same hierarchical level talk to each other over a shared message bus. And then we have a decentralized agent, which is a standalone single agent app that doesn't have full connectivity to the centralized ADMS system. On the next slide, we have a high-level example of distributed apps being deployed first to the simulation environment and second to a field environment. And in these cases, we have field buses, which again are local area-specific buses where field devices are connected to one local field bus. And distributed apps can talk to those devices over those field buses. Again, in the simulation environment, the field buses are inside GridAPPS-D. On the field environment, the field buses are outside of the centralized GridAPPS-D environment. In each case, if we have coordinating agents are the top-level agents of a hierarchical distributed app architecture. Those coordinating agents talk to the centralized operational technology bus, again, over the standardized API. On the next slide, there are data flow diagrams for two categories of distributed app architectures. First, we have apps with a coordinating agent. Again, a coordinating agent talks to the centralized OT bus, and that's reflected. You see the orange distributed app blocks showing connections on the left-hand side to the OT bus in blue above that. So we have app output data and app configuration data going to and coming from the OT bus respectively. Distributed apps in either case can receive status and measurement data from field devices over a field bus, and they can control field devices to the extent that they're controllable over the field bus as well. And for each field bus, we have a context manager, which allows apps to optionally self-configure using local context data if they don't have that coordinating agent, as shown on the right-hand side with the green arrows. And it also allows distributed agents. So each distributed app here is a collection of agents, whereas we've shown agents separately on the distributed app architecture slide. But the complete app will have agents that are, go ahead.
Did you advance? My internet dropped out on me for a second.
I
was still on the distributed data flows.
Yeah.
Distributed data flows, correct? The distributed data flows slide. Okay, just wanted to make sure.
Thanks. I think we have some audio delay. Okay, thanks, Alexander. So the context manager allows apps to stay appraised, local agents to stay appraised of what's in their local area, even if there is a coordinating agent hierarchically above those distributed agents that has a broader view. On the next slide, we have a distributed app API diagram. This is a draft, but this shows some UML of the classes that the distributed app API is implemented using. These are Java classes, but I don't want to go into individual functions here, but basically there's a field bus object shown at the lower center there, and then a field device interface shown in the upper left. And the field device interface allows, it connects to the field device and provides a standardized way of interacting with individual types of devices. And then the distributed agent is shown in the upper right, and that represents the API as seen by the distributed agent code itself. So the code lives in an agent piece of software, and then it's represented inside the API by the standardized interface. On the next slide, I'll introduce a little bit more detail about message buses, and I want to distinguish that from communications infrastructure. So we have three layers of abstraction here. On the bottom, there is communications infrastructure, which is composed of hardware, and it can be as redundant as the communication system allows it to be. On top of that, we have message buses, which are constructed virtually on top of the communications infrastructure. So you can imagine if we have a partial communications outage, we might have message buses that are also fully in outage if all of the equipment associated with the area under the message bus, if all of that communications equipment is out, then that message bus will also be in an outage state. It is also possible that an individual message bus might be in a partial outage state if some of its equipment is outaged, or it may be fully operational even if communications infrastructure elsewhere in the system is out of service. And then on top of that, we have apps and agents. So apps and agents interact with message buses that do not map directly to communications infrastructure, but are rather layered on top of it. So with that in mind, on the next slide, I'm transitioning from the distributed app architecture, which is generalized, to the distributed app API that we've implemented in GridAPPS-D. And when we implemented the architecture in GridAPPS-D, we had to choose layers that were defined by physical equipment to represent the app hierarchy. But this is not required organization of equipment or layers. So layers could be defined differently, and they would still meet all of the objectives of the distributed app architecture and the ability to support distributed apps. So here we have shown a very simple feeder on the right-hand side, and this, of course, there are multiple feeders, but this represents the distribution system message bus. There's one distribution system message bus for all feeders on the distribution system. If you can advance, Alexander, we'll see a feeder area message bus. So we have a message bus for each feeder in addition to that distribution system level message bus. And then we start to have equipment associated with the feeder level message bus. So we have an onload tap changer at the substation that GridAPPS-D will associate with the feeder area message bus. And then we have switches that are also associated with the feeder area message bus. Then at the next layer, if you can advance, Alexander, we have the switch area message buses, and we have 3 shown in our diagram to the right. Each of those is defined by the area that would be an island, either powered or not, if you opened every switch in the distribution system. And attached to these switch area message buses, we have medium voltage equipment, including capacitors and medium voltage DER that might be utility owned or customer owned. If you could advance one more time, Alexander, we have distribution secondary message buses. So at each distribution transformer, we have everything downstream of that inside GridAPPS-D mapped to the distribution secondary message bus. And all of the low voltage assets, including any customer owned assets, DER or dispatchable load, would be included there. On the next slide, there are examples of distributed app architectures as shown mapped to these GridAPPS-D message buses. So I showed some conceptual architectures above, and now we've mapped specific application architectures to the layers that exist in GridAPPS-D. If we had different layers, then this mapping would look a little bit different. On the left, we have a distributed state estimator where we have, starting from the bottom, secondary agents that can solve state estimation on a local area. And then we use a multi-area state estimation approach to combine those state estimates with a feeder area message bus estimate. And the feeder area message bus estimates everything between the substation and the distribution transformers. And then using the multi-area framework, we can produce a full system state estimate at the coordinating agent level. And you see a pass-through agent at the level between the feeder message bus and the switch area message buses. And that's because this app doesn't use any logic at the switch area, but rather it uses the pass-through agent to allow the feeder agent to communicate with the secondary agents. On the right-hand side, we have a distributed energy coordinator, which similarly has two levels of functional agents and then a pass-through agent. The top level, well, again, starting at the bottom, we have a pass-through agent that allows devices to be accessed by the level 2 agents. The level 2 agents coordinate devices underneath them and then are combined at the top level to produce a unified coordination scheme for one feeder. And then again, we have a coordinating agent to configure all of the agents below them. On the next slide, I have a few results from a demonstration proof of concept of the distributed state estimator. This distributed state estimator, it is designed to allow state estimates to ride through partial outages, like we discussed before. Measurements and the true state, TS, in the black line on the left there, are shown. So the measurements obviously have some noise on top of the true state, and the measurements are what's fed into the state estimator. On the right-hand side, we show measurement error compared to estimation error, both for a centralized state estimate in red and a multi-area state estimation in blue. This particular state estimation algorithm was implemented using an approach that was optimized for execution time, so that a full feeder state estimation at the centralized level could be solved within a couple of minutes, even for a complicated system. So we do introduce additional error here when we go to the multi-area state estimation. It is mathematically possible to eliminate that error if we use optimal state estimation. We're looking into doing that, but it looks like there will be a significant execution time trade-off there. So we'll have a decision to make about whether we decide to have a trade-off between distributed solutions and execution time. On the last slide that I have, we have some results for the distributed energy coordinator. This application coordinates distributed energy resources to make sure that local voltages are within ANSI limits, so between 0.95 and 1.05 per unit. And this particular approach uses fairness metrics to make sure that individual devices, in order to achieve their shared objectives, are not repeatedly cycled. So we want to achieve coordinated results while having the burden on each device be fair. We've considered 3 definitions of fairness that I won't get into in detail here, but we definitely acknowledge that there's more than one conception of fairness, and we're doing a study right now that looks at if you optimize to each of those 3 definitions of fairness individually, how do the other metrics of fairness stack up? And we also compare this to the fairness agnostic optimization, which optimizes to the physical objective without a concept of fairness. You can see the fairness-based results on the upper right 2 plots, where we have fairness factors defined, but this is basically the amount of burden that each device sees. And for the 2 top level figures, the fairness factor or the burden is shared evenly among all devices. On the bottom, we're fairness agnostic, and you can see that some devices are contributing significantly more than others to the solution. The bottom left plot shows the fairness-based solution, where not all of the lines are exactly at 1.05 in the optimal solution because of that separation due to fairness consideration. So those are a couple examples of distributed apps and what we can do with the distributed app API. And with that, I'll turn it over to Jim for some concluding remarks.
Jim, do you want me to just advance the slides for you, or will you reshare?
Sure. I guess we might as well. I'll go ahead and share and give you a chance to take a look at some of the chats, maybe, Alexander.
Okay, sounds good.
And let me see if I can indeed successfully do that. Get this into presentation mode. Actually, I'm going to share unscripted. I'm going to go off script here. So I'm going to, my name's Jim Ogle. I'm the PI for the GridAPPS-D project. I'm fairly recent in that role. I've worked on GridAPPS-D for a number of years, both within PNNL and was an advisor prior to joining PNNL 3 years ago. I wanted to share, Alexander brought up some of the applications that have been developed and some of the people that have been working with GridAPPS-D in the earlier stages. In the last year or so, we've had quite a bit of engagement from other developers that are using the program. You can see here across multiple DOE programs, there's a variety of projects that are leveraging GridAPPS-D as part of their, that platform for the research and development and analysis. A number of national labs are developing applications. And what I think is particularly interesting and kind of demonstrates some key capabilities that can help the research community is on some of these projects, like the FAST DERMS project, which is a GMLC project. There's 4 labs and a university that are all developing their own application that's part of an integrated solution. And those applications have to work together and eventually kind of integrate together to see how the, in this case, DER coordination is going to react in the real world. So in that example, using the GridAPPS-D platform, the developers from Oak Ridge, from NREL, from Lawrence Berkeley National Lab, they're able to develop their applications, their controls, their applications in the GridAPPS-D platform in their local environment. Then we've got an environment where those applications come together and start interacting with each other, where we can simplify that integration by using that standard API. And then a number of universities have started up projects, and I'm going to talk here specifically about Washington State University collaborations. So let me get to the other slides here. So hopefully you get a feel for what GridAPPS-D is now, and some of the features and capabilities that can contribute to the research community and industry. A key point is what I brought up there in the examples with the different labs with the research projects that are going on right now, and that ability to really kind of look through that life cycle from early research through development and eventual deployment. And this really, as a platform, this has that network effect, in that the more people that join and contribute to applications within this platform, this ecosystem, the better benefits it has, the greater impact it can have as you leverage the work that other people have contributed to and can build off the services and capabilities and data that's available from some of those other applications. Ways to get engaged here is we're going to have a GridAPPS-D kind of open house later in 2022. We have a specific kind of topic working group with the distributed applications, which Andy covered the work that's going on there. If you're interested in that particular topic, please reach out to one of us, and we can get you engaged with that team. We had a kind of a year-long workshop seminar last year, and are looking at spinning up a new topic within that working group this very shortly. Then there's a number of developer meetings and app developer meetings talking about Toolbox, weekly working in debug meetings. Lots of ways to get to join up and be engaged. WSU and PNNL have had a great collaboration in this GridAPPS-D project from the very beginning. As you saw from Alexander, WSU was developing some of the initial applications that were part of the early platform development phase. Looking towards the future, we're working and collaborating with WSU with specific kind of focus right now in that distributed application area. So WSU, we're doing some research around different ways of decomposing these distribution optimizations and control functions in that layered kind of approach. And the first application that they are developing is just a distributed resilient DER assisted restoration approach, where that process of restoration is broken down into 3 different layers in this example, where at the high level you can have full observability, look at switch level aggregation, and then work down at different levels where each kind of area, switched eliminated area, can optimize the restoration and the resources within that area. But together they cooperate to serve the objectives of getting the most load served as fast as possible. Along that line, moving on beyond just that particular application, we are going to be working with WSU, looking at some of those other kind of optimizations within that distribution operation space, and exploring different ways of decomposing those problems. And in particular, of interest here is that as we think about those applications with different agents that are working, independently but cooperating to solve, overall system objective, the question comes to mind: how do we make sure that those different agents, applications that are working on, a particular objective, don't have hidden couplings because they're connected to that same physics, the physics of the physical network, that they don't end up kind of working cross-purpose to each other and unknowingly impact, the optimization and behavior of another application, and in the worst case, result in a unstable system operation. So we've got some work planned out looking at how to evaluate the sensitivities between the different applications, and how to organize, structure, and coordinate so that we can make sure that there aren't impacts related to any conflicts that may arise. Another area where we're collaborating in this project is looking at kind of beyond that, the optimization and the power system side, looking at how do we coordinate between that power system control and the underlying communications that need to support these new kind of data flows and information exchanges, as well as the dependency as we put intelligence out on the grid edge with the compute that may be available. Where is it available? How much is available? And how do we kind of look at that co-design, if you will, or at least co-optimization between those 3 different dimensions of the problem? So this is a work that we're just kicking off here this month with the WSU, or as soon as the paperwork's finished, where we're going to be looking at the power system point of view, and WSU is going to continue on some of these, looking at the distributed approaches and comparing kind of centralized, distributed, decentralized approaches, and the different types of communications, compute, impacts that those different choices make, and also looking at them spanning from across kind of blue sky to dark sky, to different modes of operations of the grid, and see how that changes the communications and the service requirements. So this work kind of will bring in new dimensions into this distributed space, and also bring in some new capabilities within the GridAPPS-D platform, as we'll be tying in a communication simulation as part of this effort. So that is the end of my conclusion here and the end of our presentation. We've greatly enjoyed and benefited in the GridAPPS-D project, the collaboration of WSU, and PNNL. And as mentioned, the more collaboration, the more projects we can get within this particular GridAPPS-D project, the more value the platform and that ecosystem will bring to everyone here. So,
Great. Well, thank
Anamika?
you very much, Alexander and Andy and Jim. That was great. We really appreciate you sharing details of the project and highlighting the collaboration, not only between WSU and PNNL, but also showing the linkages to other organizations that were collaborating in this broader space. And I also want to thank Alexander for responding to several of the questions in the chat. So that's great. And so I think he still might be catching up to all of the questions, but if there's any additional questions, please feel free to get those in the chat, and we'll work on responses to those. We have 3 minutes if somebody would like to raise their hand and ask a question verbally. We can also accommodate that. So just check for hands here, see if I see any. Okay, Sanjeev, go ahead.
Yeah, thanks, Alexander and the team. So it's a great presentation. I just wonder about the application side of it. I mean, did you test with any utility or co-op where you can just test these applications directly with the DMS or maybe in parallel with those, so that you can compare the performance of the GridAPPS-D?
You want to take that one, Jim, or should I?
So there's been in those early applications, there was an application evaluation process that took place, and that actually took place in the EIOC operating center at PNNL, where those applications in partner with utilities and utility system operators actually kind of went through a process of seeing how they would work. We're in early discussions with a couple utilities looking at actually deploying this in their planning environment and potentially some operational environments, these applications, but those have not yet been deployed. And finally, I'll mention as part of the work, we have done the integration with some commercial tools like surveillance, ADMS system, working with some of these applications through that standard DNP3 bus. So hopefully that gives you a sense of kind of where we're at in terms of those real, kind of more real evaluations.
Yeah, thank you.
Okay, thanks for the question, Sanjeev. I think in the interest of time, we probably don't have time to accommodate anymore. So Alexander, if you just want to keep typing away and finish answering the questions to the chats that have come in, and I'll just thank everybody for your participation in today's webinar. And thanks to our 3 terrific speakers that gave us the comprehensive information about this project. And we look forward to not only continuing your participation in the weekly ESIC seminars, but also the monthly ESIC seminars that will be hosted by the Advanced Grid Institute. Dr. Schultz, do you have any closing comments?
No, thanks everybody. This was very informative. We had a great crowd, so we appreciate your time. I know it's a busy week with ISGT, T&D, and everything else. So thanks so much for presenting.
Very welcome.
Okay. Have a good rest of your day, everybody.
Thank you. Andy, I'm wondering if you can answer Sanjeev's last question. I think